I really want to understand what are the genetic underpinnings of lifespan. And one way we can do that is we can genotype all the mice and we can do a genome-wide association study. We're going to map loci in the genome that are associated with lifespan. And a mouse has 19 autosomes and an XY chromosomes and a mitochondria. The height of the peak here is showing me the strength of association of a particular point on a chromosome with lifespan. And the higher the peak, the stronger the association with lifespan. So there's this really high peak here on chromosome 18, I'll come back to. We can also calculate how much of the variability in lifespan is explained by different factors. You remember that lifespan is a really noisy trait. It was even for the 40% CR mice, there were short-lived mice and long-lived mice and a lot of variance. And it turns out that diet explains about 7% of that variance. And then after accounting for diet, body weight, which we talked about a lot, that comes in at around 1%. Chromosome 18, just all by itself, explains 4.5% of the variation in body weight. And the rest of the genetic background, all this stuff out here that really, we can't sift out. There must be dozens of loci that are affecting lifespan. Together, the genetics is explaining about 20%. So if you're a mouse, if you're a DO mouse living in these happy conditions, this is the breakdown. There's a whole other lecture to explain why it's more complicated in humans. But diet has an effect. It's a huge effect, but it's dwarfed by genetics. Interesting that chromosome 18 locus is not only a lifespan, we call them quantitative trait loci. It's not only associated with lifespan, it's associated with RDW. Weird. We have a working hypothesis right now that this locus on chromosome 18 affects something that's closely related to RDW, which affects lifespan. So we have a causal hypothesis and some ongoing studies that I hope will resolve this eventually.